All right, everybody. You're coming to me today to learn about something called a definite integral. You're going to learn some new symbols, you're going to learn some new ways of calculating stuff, but it all comes back to one basic concept that you're going to try to keep track of for the rest of the course. But before we get there, I want to introduce to you something called sigma notation. Sigma notation is also known as summation notation, and when you have sigma notation, it's called sigma notation, by the way, because this is a capital sigma. If we are talking about the summation from k equals 1 to n of a sub k, what we have to do for each number from the initial number up to the final quantity, the index and the limit here, we want to evaluate the expression at each individual number between those until we reach the top number. So you can see in that example, we have the summation from n equals 0 to 3 of 2n squared. So we start with n equals 0. We evaluate 2n squared for 0. So notice that first term right over here, we have 2 times 0 squared. And again, it's also called summation notation, so we add to it the next number evaluated. So 0, 1, 2, 3, and then we actually evaluate all of those expressions, add them together. The summation here would be equal to 28. I want you to take a quick pause and just look at page 282, the quick review. I'll even put it up here for you guys, right over Chahira. You can see, quick review, sorry. It's this blue section right up here. So try to complete those problems. Pause the camera and then come back to me. I'm gonna pause right now. So you can actually see I have the answers here for you if you want to check your answers. Notice in 1 through 3, it's really just evaluating the expressions. In 4, 5, and 6, you're trying to set them up as some sort of sigma notation. It doesn't matter what letter you use. You can see in these cases they use K. Sometimes they use N. Sometimes we use I think I've seen J's in there before. Yeah, there's a J right there. So it doesn't matter what what letter you use. Typically, we don't use X for it, although I do see over here we do have an X. Yeah. So there's your answers, and let's go forward. As I said, this section is called the definite integral. So section 5.2, definite integrals. I'm trying to bring this back to the rams that we had from yesterday. Rams, again, I think I brought this up, but there is another word for it. It is also called a Riemann sum. This is bothering me, so I just need to fix it real quick. I spelled Riemann's name incorrectly. Riemann has 2 N's in it, so Riemann sum is another name. The width of the rectangle, we used this term yesterday. It's called a subinterval. So in this case, you can see each subinterval is equal to 1 unit. The entire interval is called the partition. So you've got the subinterval, are these little tiny pieces in here, versus the partition being the entire interval that we're concerned over. What we have to look at here is the subintervals do not have to be the same size. So you can have varying sizes of subintervals. That being said, we have to have something called the longest subinterval. So if the partition is denoted by P, then the length of the longest subinterval is called the norm of P. And then the way that we write the norm of P is just these double absolute value brackets around a P. As the norm of P gets smaller, so as the longest subinterval gets smaller, all of the subintervals get smaller, and therefore the approximation for the area gets better. We addressed this yesterday when we had more subintervals. We have better approximations, meaning more subintervals, smaller subintervals, and the norm gets smaller, we get a better approximation. Down here is how we have to write out what the area is underneath a curve. So the area is the limit as the norm of the partition approaches 0, meaning it gets as small as possible, of the summation from k equals 1 to n of f of c sub k times delta x sub k, if p is a partition of the interval from a to b. I'd recommend putting that in my notes if I were you. Now, there is another way of thinking about this other than the norm getting smaller. So the smallest interval getting, or the biggest subinterval getting to the smallest size possible. We can just think of it as having an infinite number of subintervals. So an infinite RAM is what we're going to call this. So up here, this expression is exactly what was on the last page. We can see down here that as n approaches infinity, the limit as n approaches infinity of the summation from k equals 1 to n of f of c sub k delta x is called the definite integral. So that is the definition of a definite integral. A definite integral is a Riemann sum with infinite rectangles in it. So an LRAM, an RRAM, an MRAM, it doesn't matter which one it is, because when we have infinite rectangles, the rectangles are infinitely skinny and all the values end up being the same, which is the exact area. Now Leibniz, when he was discovering calculus, realized that writing like this is kind of annoying, especially considering we don't even acknowledge what the interval is in this expression. So we shift from the finite into the infinitesimal, just like when we talked about switching from delta y over delta x to dy dx to get our derivative notation. Here we can shift from sigma to the Latin equivalent and this delta to the Latin equivalent in order to produce our notation for the definite integral. So the definite integral, instead of talking about the limit is going to be boiled into this symbol. We take the sigma and change it to its Latin equivalent. Its Latin equivalent is a stretched out s. So we have the integral from a to b. We've now acknowledged the interval over which we are calculating this, of f of x. And when we get to this delta, instead of calling it a delta, we change to the Latin equivalent. It's going to be our dx. So right there, you are seeing for the first time the definite integral notation. Some of you have probably seen the integral symbol before and you didn't know what it meant. Now I am telling you that this symbol, integral from a to b of f of x dx, means the area under the curve between a and b, just like we calculated in, or estimated using our RAMs. So again, here it is laid out for you. Very small change in x becomes dx. It is essentially our differential from last chapter. I will point out that a lot of people, when they are working with integrals for the first time, consistently leave off the dx on the integral notation. Please don't be that person. It's kind of like finishing up the integral notation. In order to have an integral symbol, you need to have the differential at the end. So again, some terms for all of these things. We have the upper limit of integration, the lower limit of integration. We've got the integration symbol, the integrand. The integrand is going to be the function that we're concentrating on. So the integrand is everything between the integral symbol and the differential. Where it says variable of integration, it is just referring to the x right there. You will see many times throughout the units that we were covering integration, you will have different variables other than x. Whatever the variable is after d, that is our variable of integration. It says it's a dummy variable because the answer does not depend on the variable chosen. You're going to see d thetas, you're going to see ds's, all of those pop up. So don't worry about that variable. It just means the variable integrand has to match that. And again, as we proceed, this is going to become easier. This is the first time that you've seen integral notation. So here, if we've got if y equals f of x is non-negative and integrable over a closed interval from a to b, then the area under the curve y equals f of x from a to b is the integral of f from a to b. All right, so that's important to notice. Or to know, it is talking about non-negative functions, so we're only talking about functions above the x-axis. There's something different that happens when we have functions below the x-axis, and it's going to be kind of weird for me to say it, but you'll see that in just a minute. Down here, we actually calculated an integral, an exact integral, last class. This integral is the integral from 0 to 4 of this function right here is a constant function. So that function is going to be 3. And then we have to close it off with the differential, dx. So that equation, that definite integral right here, is actually solved using this math right here. And the reason it is solved with this math right here is because this expression just means take the area underneath this curve from 0 to 4. When we draw it out, we get this rectangle. If you don't know how to find the area of a rectangle, well, come see me. It's length times width. That should be enough for you guys to understand what the area of a rectangle is. And actually, this allows us to see how to calculate the definite integral of any constant function. If f of x is equal to c, where c is a constant on the interval from a to b, then the integral from a to b of f of x dx is equal to the integral from a to b of c dx, which is equal to c times the quantity of b minus a. That's a lot of stuff. You can memorize that formula if you want to, but basically every time I do a problem like this, if c is a constant, I draw the constant. A is my lower limit. I draw it in there. B is my upper limit. I draw it in there. Every time if I have a constant function, since my lower limit and upper limit are just going to be vertical boundaries here, I'm always going to get a rectangle. The height of that rectangle is going to be the c. The width of that rectangle is always going to be b minus a. So that's how I work it, but you can also memorize the formula. Now here's where we get into a little bit of weirdness. You can see that we have a constant function that is negative. So that constant function, all of the area is below the x-axis. We enter a concept of negative area. Remember when you were in geometry, we said there's no such thing as a negative area. Area is always positive. But here we have a concept of a negative area. If the figure exists below the x-axis, then the definite integral is going to be negative. And you can just see that from here. The constant was negative c, so the answer is going to end up being negative. All right? Move on a little bit. Non-constant slopes, no problem if you know geometry. So let's look at these two problems. In these two problems, the easiest way to do this is to graph the function. So let's just look at this first one right here. The integral from 0 to 4 of 1/2 t plus 1 dt. I'm trying to be deliberate with you guys right now, where I read each integral out loud so you're exposed to how to read the integral as much as possible, because I often hear people asking me to do a problem, they try to read it and they don't know how to read it. So again, integral from 0 to 4 of 1/2 t plus 1 dt. Notice I didn't need to read the parentheses because the dt implies that the integrand is over there. Now, beyond that, I have to be able to graph this in order to find out what this value is. Looking at this, I know that 1/2 t plus 1, okay, so that's going to have a y-intercept of 1 and a slope of 1/2. I know that I'm starting at 0 and I'm ending at 4. So I know that I'm going to have to include this point. And 1, 2, 3, 4, 5. I think that's going to cover it. 1, 2, 3, 4. I know that's going to cover it because I know that I'm going from x equals 0 to x equals 4. Slope is 1/2, so I go up 1 over 2, up 1 over 2. Okay, cool. There's my line right there. Now what I look at here, I want to draw in my, my lower limit and my upper limit. I'm going to put this in a different color just so that we can see it. The lower limit is at 0. I put a vertical line right there. Upper limit is at 4. I put a vertical line right there. This operation where I say the integral from 0 to 4 of 1/2 t plus 1 dt just means I want to find the area between the curve and the x-axis. Since the curve is entirely above the x-axis, I know that the answer is going to be positive. If this was down here, it would be negative. Basically, if I color in this shape right here, I want to find the area of that blue shape. And however I find the area of that blue shape, that's going to give me the value of the definite integral. Probably the easiest way to calculate a definite integral if you remember geometry. Now here, I see that this is a trapezoid. If you didn't see that this was a trapezoid, you could split it up into a rectangle and a triangle. But here, since I know that this is a trapezoid, the area formula for a trapezoid, just going off the top of my head, I remember this from what's that course? Oh, it's my second favorite course to teach, geometry. It's 1/2 the sum of the bases times the height. So if you forget the area formula for a trapezoid, maybe write that down so that you don't forget it anymore. Now looking up here, I can see my two bases, the parallel sides, have a length of 1, and it looks like 3, right? 1 and 3. So I'm going to have 1/2 times the quantity of 1 plus 3 times my height. And my height is the non-parallel side. The non-parallel side is going to be 1, 2, 3, 4. 1/2 times 1 plus 3 times 4. I'm going to get a grand total of 4, half 2, 8. The answer there is 8. The integral from 0 to 4 of 1/2 t plus 1 dt is equal to 8. Awesome. Yay. Now looking over here, I've got the integral from -3 to 3 of the square root of 9 minus x squared dx. Again, this is going to be it's going to be helpful if you know how to graph certain things. Like I happen to see that the integrand right here is in the format of y is equal to the square root of r squared minus x squared. I happen to know that this is the equation of a semicircle. What happens if I don't remember that that's the equation of a semicircle? Well, okay, why don't we just grab this lunatic right here? Looking at this lunatic right here, I can go into my y equals menu and let's clear out these two. I can graph the function, the second square. Nope, that wasn't it. Second square root, nope. Why is it not working all of a sudden? Second square root, there we go, of 9 minus x squared. I know that I'm going, oopsies. I know that I'm going from -3 to 3. How do I know that? From this Joni right up here, lower limit to upper limit. Let's make our y min, I don't know, let's just make some consistency, -3 to 3 as well. And then when we graph it, hey, look, it looks like a semicircle. If I have trouble with it's not exactly the right aspect ratio, I could go into my zoom and hit zoom square, and all of a sudden I can see that it is a semicircle. Again, I wouldn't even personally touch my calculator for this one because I know how this function works. I know that this is the graph of a semicircle. And actually, you're going to know from now on, if you have the square root of blank minus x squared, that's a part of a circle here. Looking at this, I see that the radius is 3 because r squared is 9. So I'm going to go out 3 units here, 3 units here, and 3 units here, semicircle. And again, just to clear up where I'm talking about my area, I'm going to color that middle part in here. I'm starting at -3, I'm ending at +3, and I want to get the area bounded by the curve and the function. So look in here. That's all of this stuff right in here. I want to find the area of the red figure right here. Area of that red figure, it's half of a circle. So the easiest way to calculate my integral from -3 to 3 of the square root of 9 minus x squared is going to be half the area of a circle. And we should know that the area of a circle is pi r squared. 3 squared is 9. This is going to be 9/2 pi. Done. There we go. Easiest way possible to calculate a definite integral, if the figure ends up being geometric. And we should know that not all figures end up being geometric figures. Now look in here, we've only dealt with positive functions, except for that one time where we had that constant that was below the x-axis. I already mentioned this, but the area is the opposite of the definite integral if f of x is below 0. If f of x is both above and below the x-axis, you want to do the area above the x-axis minus the area below the x-axis. Down here, I actually have some functions some definite integrals already laid out for you, and the graphs drawn for you. Actually, this one doesn't go quite far enough. The grapher just didn't have the capability of going all the way to the x-axis there. So looking here for the integral from -3 to 3 of the negative square root of 9 minus x squared dx, it's just talking about this area down here. Again, coloring it in to help us see it, we're talking about this red space down here. Again, I see that that is a half circle. Area of a half circle is going to be 1/2 pi r squared. Since that red figure is below the x-axis, I'm going to be talking about the concept of a negative area. So this is going to be equal to -1/2 pi, and again, I see this set up, I know that it's a semicircle with a radius of 3, so this is going to be -1/2 pi 3 squared, which would be equal to -9/2 pi. So be on the lookout for anything below the x-axis negative area. Looking here, we're going the integral from 0 to 4 of -x plus 2 dx. That means putting in my limits here. My limits before were just at the x-axis. Here, I've got a vertical line at my 0 and a vertical line at my 4. In order to calculate this area, I want to kind of, when I draw this in, it'll be kind of like a crooked bow tie shape here. Makes me feel comfortable. So here, in order to find this, I need to take the area above the x-axis and subtract the area below the x-axis. So looking at this above the x-axis, I've got a triangle. My triangle has 1/2 base times height. Base is 2, height is 2. 1/2, 2 times 2, minus the area of the bottom of the triangle below the x-axis. Still going to be 1/2. Base is still 2, height is still 2. Well, looking at this, I don't even need to do any arithmetic here because I see these expressions are the same. I'm subtracting them. This is going to be a 0 integral. Again, all we're talking about in this section is definite integral means calculate the area. Find the area however you know how, and as of right now, the only way y'all know how to do area is by using geometry. Again, that's not going to allow us to find every definite integral, but definite integration is a very big concept that we're going to have to take a while to tackle. All right, let's move forward here. Whoo, man, this stuff. I did give you the answers. This is exploration 1 on page 279. I just gave you the answers. You really do have to look at exploration 1 on page 279 to understand this. So let me pull that up here. And now you guys can see it's perfectly framed in my doc cam here. In order to be able to do any of this, you need to read this first sentence that says, it is a fact that the integral from 0 to pi of sine of x dx is equal to 2. How do I know that? Because the book says it is a fact. We'll come back to it later, and we will show you why the integral from 0 to pi of sine of x dx is equal to 2. But right now, just take that for granted. That means from 0 to pi, underneath the curve, this area right in here is 2. This half football shape that we have right here is 2. With that information, with what you know about integrals and areas, what you know about graphing curves, and sometimes a bit of intuition, you can actually figure out all of these values throughout here. So I'm going to switch back to my smartboard here to show you some of that stuff. So you can see some things that I've drawn on my flip chart over here. I've actually put the given information that, again, I only know this because the book told me it. I actually drew the picture that the book gave me, and I put the 2 in that half football shape just to remind me that red area is 2. And I start trying to figure some stuff out, like here, I've got the integral from pi to 2 pi of sine of x dx. Well, when I look at the graph from 0 to 2 pi, kind of looks like this, where I happen to know that this is at pi. I know that this area right here is 2, so this area over here is congruent to this little half almond shape here, so I know that this is 2 as well. The area is 2, but since it's below the x-axis, this value, the integral from pi to 2 pi of sine of x dx, is actually negative 2. Try to use these kinds of concepts to answer the rest of these questions. Pause the video and come back in after you try to do these problems. So I'll stop, and I'm picking up from here. Number 2, I'm talking about the integral from 0 to 2 pi. So again, going back to my picture up here, I've got the 2 up here, I've got the negative 2 down here. Since I know to find the area when I have the curve both above and below the x-axis, I just want to take the difference of the 2 areas. These areas cancel each other out, just like that bow tie shape that we had from a couple of slides ago. So this integral from 0 to 2 pi of sine of x dx is going to be equal to 0. Let's look at some other ones. Ooh, integral from 0 to pi over 2 of sine of x dx. Looking at that, that's going to right here. That's going halfway through the almond shape. So halfway through the almond shape, and since I'm splitting this symmetric shape in half, I'm going to get 1 for the integral from 0 to pi over 2 of sine of x dx. This one down here, number 4, is probably the most missed problem that I've seen ever as far as interpreting graphs with definite integrals. Let me show you what happens with number 4. So I'm going to draw the graph of 2 plus sine of x. Give me 1 second to draw that. Like I said, give me 1 second to draw it. I'm not drawing it. So that plus 2 really shifts the graph up 2 units. So what I can see here is I have my half almond shape, that 2 is sitting right up here. That's where this 2 comes from. But that 2 pi, I have to look at what that almond shape is sitting on top of. And that almond shape is actually sitting on top of a rectangle, and that rectangle has a height of 2 and a base of pi. So when I multiply my 2 times pi, that's where that 2 pi is going to come from when I'm evaluating my definite integral. When I look at number 5, the integral from 0 to pi of 2 sine of x dx. If I remember what that 2 does to a sine function, it should increase the amplitude by a factor of 2. Let me draw that picture for you again. I'm really fast at drawing these, aren't I? So we can now see that I've increased my amplitude to 2. That means I just take this almond shape up here and stretch it out by a factor of 2, which is why the integral from 0 to pi of 2 sine of x dx is equal to 4. Back over here, the integral from 2 to pi plus 2 of sine of x minus 2 dx. What we have for that minus 2, let me just show you real quick. Man, how do I draw these so quickly? That's just amazing. So what I see here is I have the same half almond shape as up here. It's just been shifted over 2 units. Since I'm shifting my limits over 2 units as well, the area ends up being the same. So the integral from 2 to pi plus 2 of sine of x minus 2 dx is equal to 2. Now looking at number 7, you can see we have our first change of variable here. Don't be scared as long as these two match. We good. Now we're looking at the integral from negative pi to pi of sine of u du. Let me graph that real quick just so we can see what happens. Oh hey, it's almost the exact same thing as what happened in number 2, except now it's really focused around the origin. We still have the half almond shape up here, half almond shape down here. We end up with the 2 cancel each other out. You got 2 up here, negative 2 down here, you get 0. Looking at the integral from 0 to 2 pi of sine of x over 2 dx, we need to think of what that divide by 2 does to a trig function. If we remember from last year, we had that 2 pi divided by b. It was the period of the function is changed when you change the inside of the trig function. Let me draw that for you real quick. So that dividing by 2 inside of the function actually stretches out that half almond shape. We've got a longer almond shape. Since the base is twice as long, it increases the area by a factor of 2. We get 4 off of that one. And the integral from 0 to pi of cosine of x. Okay, fine. I'll show you guys how it's made here. Cosine looks like that from 0 to pi. If I look at that shape, I've got half above and half below. They cancel each other out, which is why the integral from 0 to pi of cosine of x dx is equal to 0. Again, without knowing this information right up here, you can't do any of this problem. The only way that you know the integral from 0 to pi of sine of x dx is equal to 2 is because I told you. So if that ever pops up on a quiz, that's an easy question to answer. It's just 2. Let's look a little bit further. Ooh, let's try some integrals that are harder to calculate. Man, I forgot that this popped up, this section. Man, I didn't want to give you guys this yet. You guys don't want to know how to use your calculator to approximate a definite integral, do you? Okay, fine. I'll show you. So I'm pretty sure you all know that this is a calculator, right? So this is my calculator that I have. Let's see, why is it? Oh, okay, there we go. Now you can see the full screen. I go to my home screen, and if you have a TI-84, there's 2 ways to get a numerical integrator. One way to get the numerical integrator is by hitting alpha, window, and looking right down here at fn_int. When you do that, you can see that the setup to the numerical integrator is exactly as you have the setup in the problem. You just type it in exactly as it's asked to you. The other way to get to the numerical integrator, and those of you who have a TI-83, here is how you have to access it as well. It is in the math menu, so you hit math, and you go all the way down to option number 9. If you have a TI-84, doing this either way is going to work, whether you do alpha window or math 9. I like the pop-up windows, so you will always hear me saying alpha window 4 for that one. Now, just to be clear, we just talked about the integral from 0 to pi of sine of x dx. We knew that was 2. We can now do the same thing, alpha window 4 from -1 to 2 of x sine x dx. Enter. 2.042, well, 2.043. There are some issues that I see with this type of problem, like it's not exactly dead on. Sometimes calculating the numerical integral is going to take a little bit longer, and you might end up with a wrong-ish answer. Like if I'm remembering from earlier, we had alpha window 4, integral from -3 to 3 of the square root of 9 minus x squared dx. So that takes a while. That takes a while to do it. And here the actual answer was 9/2 pi. We can see the answer is wrong-ish out here. I mean, it's well past where we would actually have to round for AP. But I mean, just having not the exact answer is just kind of wrong for me. The reason why it's not the exact answer, your calculator is actually taking a rectangular approximation, just making the boxes really small. Yeah. So it's doing it the wrong way, but it's getting close enough. Now I do know some of you have TI-83s, so let me switch my calculator over into TI-83 mode. And magically my calculator looks like it's a TI-83. Again, I go to math, and I go down to FN int, and if you have a TI-83, it looks like this when you try to do a numerical integration. To get this into your TI-83, I'm just doing number 1 right here, so the integral from -1 to 2 of x sine of x dx. What I have to do in this case, I start by typing in the function x sine of x, comma, the variable that I wanted to use, comma, the lower limit, comma, the upper limit, close your parenthesis. And you can see I get the exact same answer as if I was doing it using a TI-84. So again, if I wanted to do math 9 of sine of x from 0 to pi, that's how I have to type it into my calculator. So let me write that on my board for you, just so that you can remember it. If you're using a TI-83 structure for numerical integration, it's going to be FN int, parentheses, f of x, comma, x, comma, your lower limit, comma, your upper limit. That only applies to the 83ers out there. 84ers, you know you have either alpha window 4 or math 9. There's how we can get to the numerical integrator. It's a nice little gift for you guys. That was the last gift I had for you. Thanks for coming in today, guys. It was special.